Hello, good morning student. This is Dr. Raheem Ahmed. Today I am going to explain you that electronic polarization in dielectric materials. We know that there are four different types of polarizations we have. Dielectric polarizations. First one is electronic polarization. Second one is ionic polarization. Third one is space charge. Fourth one is orientational polarization. In that, electronic polarization definition is very important. I have given you this definition and I will go for the derivation for electronic polarizability. Okay, definition I will go for that. Okay, no need to by head, I will take out from the figure. So electronic polarization occurs due to the displacement of positively charged nucleus and negatively charged electrons in opposite directions when external electric field is applied, thereby create a dipole moments. Dipole moments are they are creating when you are applying the external electric field. We'll check out. So what is happening here? Now I have taken one atom. We know that atom center you have the nucleus surrounding with some electrons in the orbits. Okay. Now we are not applying any field, electric field we are writing. So I consider this condition number 1 is without electric field. Without electric field means without field I have written simply. Okay. Now electrons are distributed homogeneously. Okay. Now number radius I have taken R. Okay. Then here I have to take out atomic number. Can I consider as a Z? We know that. So inside the nucleus you have the protons. You have the positive charge. Okay. So outside electron you have the negative charge. Can I write here? The center of this nucleus, can I write here? Plus ZE. Okay. So center of, due to this all the electrons, we can write minus ZE. Okay. Now both are at one place, at middle only when without electric field. We are not applying any electric field for this atom. Now both are plus ZE and minus ZE concentrated at one place only. Okay. That you have to concentrate the point. Okay, without field, so there is a two centers due to the positive center and negative center of these electrons, both are concentrated at one point. Now I am writing the charge density equation. You know that density is mass per unit volume. Can I write it here? Charge density, charge per unit volume. Density symbol is rho and charge per unit volume. Now a charge we consider that ZE, and we are knowing that due to the electron I have written minus. And volume of the sphere, you know that radius is r, then volume of the sphere is 4 by 3 pi r cube. So can I take out 3 is this side, minus ZE 3 by 4 pi r cube is equation number 1. So I will erase this thing. Why? Because it's you are not writing in an exam. Okay, minus ZE by 4 pi 3 r cube. Now when I am applying the field, electric field applying, what happened here? When I am applying the field, so actually both the centers are at one place now, clear or not? Both the centers are at one place. When I am applying the electric field, so positive charge will going to reside here and negative charge will going to reside here. Okay, both the positive and negative charge will going to reside on the plates. Now because of this positive charge, okay, this negative charge will going to attract this side. Negative center will going to attract this side. And because of this negative charge, so positive center will going to attract this side. So we consider this is the axis, the distance between these two charges. Now thereby there are two poles are created here. Means negative will going to move from this point, equilibrium position, and positive will going to move from this here to here when you are going to apply the electric field. Because there is a charge separation you have. There are two poles are created, that is called dipoles are created here. Dipoles are created when you are going to apply the electric field. Here that is the only definition, no need to by head. So in electronic polarization occurs due to the displacement of positively charged nucleus displaced from here to here, and negatively charged electrons negative electron center is moving from here to here in opposite direction. Both are in opposite direction moving when an external field is applied. Thereby dipole moment in dielectric, dipoles are created in this. Okay, dipole moment is occurred in this material, so that is called electronic polarization. From definition you have to, from figure you have to write down definition. Now So because of that, can I write it here? Actually, the positive center will going to remain here only, but we are showing here some displaced, but originally the positive center is reside here only, but negative will going to move from here to here at x distance, then it will going to create a new sphere with radius of x, Now I want to tell you that some words about this electronic polarization. So electronic polarization generally occurred in non-polar molecules only. It is in this non-polar molecules you have some polarization, but in polar molecules the polarization is zero. So see here that here what is saying here, the radius is more, the polarization is more. Why? Because this electrons, more is the electrons you have, more is the radius you have, the distance between these electrons and center attraction is very weak. Then we are going to apply the electric field, very easy to create the dipoles. The polarization is very easy to occur. The charge separation is called polarization, simple words. Okay, charge separation is called polarization. Then I have to say that more is the radius. Now the distance between these two electrons and your nucleus is very weak, then polarization is increasing that. Okay, can I write it here, equation for induced dipole moment? I will take out the symbol as mu. Mu is directly proportional to E. When electric field is increasing, induced dipole moment also increasing. Can I take out this proportionality? Then can I write it here equal? Then I will take out one constant, that is called alpha. Electronic suffix E I have taken. So alpha E equals to mu by E. What it gives you equation? When induced dipole moment is more and polarizability is more. Okay, induced dipole moment more means polarizability also more value you have that. Then we will go for, this is called electronic polarizability, alpha E. We have to derive the equation for alpha E by using this figure. Okay, can I take out like this? This is for like a children's, they are drawing like this. Okay, now I will go for here like this. I am drawing. Chalo, I am drawing like this. Okay. Now I will take out this. There are two forces are acting on this in with field. One is a Coulomb force. Try to bring this positive and negative at one position, and there are Lorentz force. Try to separate these positive and negative charges. Okay, we have to write both the equations. When Lorentz force equals to Coulomb force. Okay, Lorentz force equals to Coulomb force. When it have to say at equilibrium. At equilibrium, both the forces are equal. Now we are writing the Coulomb Lorentz force first, then Coulomb force, and we are going to equate at equilibrium this. At equilibrium. Okay. So from this you have to bring here x value. Okay, I'll equate both the one and I'll bring the x value. From that I'll substitute in this equation and I'll get you alpha E value, that we have to derive from this equation. Okay, can I go for the derivation? Okay, I'm explaining you that from here. So when you are going to apply the external field, what happened? There are two forces are there, correct or not? I said you that. So one is called Lorentz force, try to separate, and then one is Coulomb force, try to attract. At equilibrium, both are equal. Both are equal. Lorentz force equals to Coulomb force. Both are equal. Now we'll try to bring here Lorentz force first, and we'll complete Coulomb force, then I'll go to equate. See that Lorentz force is equals to F equals to QE, you know that. So F equals to QE, charge into electric field, charge into field, correct or not? So charge is ZE and electric field E applied that. So we are separating. Lorentz force means separating, that is I have taken minus ZE into D, equation number 2. Coulomb force I have to taken. So Coulomb force try to bring at one position, that's why I have taken plus. Charge is ZE and Coulomb is given that electric field equation, that is for. So we have said, we have taken the positive center is not moving from here, actually electron is moving. Then we consider the sphere here like this. Okay, for the sphere, this is the x is the radius. Okay, then I said he said that the Coulomb the q by 4 pi epsilon naught x square. We know that q1 q2 by 4 pi epsilon naught r square. We have seen that in Coulomb force. Okay, q by 4 pi epsilon naught x square is the radius, that is he's taken that. Okay, we don't know what is the q value. We know that charge density rho equals to charge per unit volume, correct or not? Suppose can I take out capital Q? Okay, capital Q I have taken. Q equals to density into volume, charge into volume. So charge from the equation number 1, charge density due to the electrons minus ZE cube by 4 pi epsilon, sorry, ZE3 not cube, ZE3 by 4 pi r cube, it is there. Okay, now the volume of the sphere is 4 pi 3 pi r cube, means x cube is there, x is there, that's why x cube I have written. Cancel out 3 4 pi will going to cancel out. The remaining what you are getting, minus ZE, okay, x cube r cube, minus ZE x cube by r cube I have written here in this equation. Q value plus ZE is same, and 4 pi epsilon naught x square is I have written here. This value I have written here. Carefully you check out what I am getting the result. I have substituted directly here. This value I substituted here. Then downside you have 4 pi epsilon x square it is there. Then cancel out x square. The remaining you are getting z into z square, e into e square, plus into minus, and you are getting the here 4 pi epsilon naught r cube. Okay, that is equation number 3. At equilibrium, Lorentz force equals to Coulomb force. I equate both the equations. Lorentz force you getting equation number 2, equation number 3. Equate equation number 2 and equation number 3. Okay, now Lorentz force is minus ZE into Z, and this Coulomb force is this one. Cancel out E, ZE. Then what you are getting here? X value you are getting. X only I will take out. All the values will bring here. That is equation number 4. What you need? We don't want X. We need that alpha E polarizability. Can I take out from the definition? Mu equals to magnitude of the charge into displacement. Okay. Now I am applying the electric field. What is happen? The charge will going to separated. Mean this magnitude of the charge. Magnitude of the charge is ZE. ZE I have written. Separation is X is there. I have written displacement. Okay. Mu equals to ZE into X. I have written. X value I got from the equation number 4. I substitute here in this equation. That is substitute equation number 4 in equation number 5. I substituted here. So I have taken place of mu suffix E I have taken ZE into ZE X. See students, I am cancelling the ZE here. Then the remaining terms I am writing for the mu suffix E 4 pi epsilon naught, okay, E 4 pi epsilon naught E r cube. So I forget to write here. So E you have to write down E. So now I have taken alpha E that constant, which constant? 4 pi epsilon naught. So r cube I have to write down as a alpha E. Okay. So 4 pi epsilon naught r cube. So I haven't written here r cube. Then I placed here E. Then I am writing here r cube. So this is known as electronic polarizability. You have seen that. So the basic equation we are going to compare with mu equals to alpha E. So in place of alpha, we have to write down, compare this left side and right side equation. In place of alpha, we are going to write down 4 pi epsilon naught r cube. Clear? This is the derivation for electronic polarizability. If you have any doubt, just you write down in your comment box. So definitely I will answer your questions. Okay.